Advanced Avionics 4.1 Automated Flight Control. Let's embark on a journey into the realm of autopilot concepts. Autopilot concepts. An autopilot serves as a valuable tool for pilots, enabling them to delegate time-intensive tasks and focus on overall aircraft and flight status. This automation assists in guiding and controlling the aircraft, handling various functions such as maintaining altitude, climbing or descending to assigned altitudes, turning to and holding assigned headings, intercepting courses, navigating between waypoints in a programmed route, and executing precision or non-precision approaches. Understanding the specific options, installation type, and basic optional functions in the aircraft is crucial for accurate operation. Advanced avionics installations typically consist of two integrated systems, the autopilot system and the flight director. The autopilot system includes servo actuators for control movement and control circuits, while the flight director acts as the system's brain. Autopilots can handle straight and level flight, but tasks like intercepting a course, changing altitudes, and tracking navigation sources with crosswinds require higher-level calculations, which the FD is designed to perform. The flight director displays guidance indications to the pilot, accepting data input from various sources, including the air data computer, attitude heading reference system, navigation sources, pilot's control panel, and autopilot servo feedback. Programming the FD is essential, as it dictates the pilot's actions. Failure to pre-program or incorrect programming may result in inaccurate flight director guidance, increasing the pilot's workload. The trade-off is that if the autopilot controls the aircraft, overall workload decreases. However, if the pilot manually flies the aircraft while using the flight director display, workload significantly increases. Regardless of the chosen approach, pilots must be aware of the flight director autopilot modes, include indicators or annunciators in their crosscheck, understand the programmed objectives of each mode, and be familiar with actions that cancel these modes. Due to the variety of available options, seemingly identical aircraft can have distinct avionics and autopilot capabilities. How to use an autopilot function. Using an autopilot function involves several essential steps to ensure safe and accurate operation. Clearly define the desired track, which could include heading, course, a series of waypoints, altitude, airspeed, and/or vertical speed. 2. Activate the desired autopilot functions and confirm engagement by monitoring the annunciator panel or autopilot display. 3. Confirm that the aircraft is following the specified track as intended by the autopilot. 4. Ensure that the correct navigation source is selected to guide the autopilot's track. This is crucial for accurate navigation and course tracking. 5. Be prepared to take manual control of the aircraft to ensure proper course or clearance tracking in the event of autopilot failure or misprogramming. Pilots should always be ready to intervene if needed. 6. Once engaged, allow the flight director, FD, and autopilot to carry out the selected and programmed modes without interference. Avoid attempting to help the autopilot perform a task, as interference could lead to false sensing of adverse conditions, potentially causing the autopilot to trim excessively and, in some cases, resulting in a total loss of control and a crash. These steps emphasize the importance of clear communication and coordination between the pilot and the autopilot system, with a focus on monitoring, verifying, and being prepared for manual intervention when necessary to ensure the safety of the flight. Specification of track and altitude. A track in aviation refers to a specific goal or reference, such as a heading or course. Autopilots are equipped with controls, including knobs, buttons, dials, or other inputs that allow pilots to specify and set these goals. The autopilot system then works to maintain or achieve the selected parameters. These goals can include not only headings or courses but also maintaining a level altitude, a particular airspeed, or a selected vertical speed with power set at a specific level. An autopilot is depicted in conjunction with conventional navigation instruments. Additionally, most autopilots come with indicators that display the amount of servo travel or trim being utilized. These indicators serve as valuable tools for pilots as they provide insights into the autopilot's activity and can serve as early warnings for adverse conditions such as icing or power loss. It's noteworthy that in normal operation, a trim indicator will rarely show full travel. Consistently observing full or nearly full travel of the trim servos may indicate potential issues such as trim servo failure, a shift in weight causing a balance problem, or airfoil-related problems like icing or inadvertent control activation. Regular monitoring of these indicators is essential for detecting and addressing any anomalies promptly. Primary flight displays, PFDs. Primary flight displays play a crucial role in modern avionics systems, often integrating controls for autopilot modes seamlessly. In Figure 4.2, a primary flight display is depicted, showcasing knobs that enable pilots to enter autopilot modes without diverting their attention from the primary flight instruments. This design enhances user convenience and ensures that pilots can manage autopilot functions efficiently while maintaining a focus on critical flight information. The integration of controls on the primary flight display streamlines the user interface, contributing to a more intuitive and user-friendly cockpit experience. Engagement of autopilot function. Autopilots are equipped with a set of buttons that facilitate the selection and engagement of various modes and functions. You can observe buttons positioned along the bottom of the autopilot, which are utilized to engage different autopilot modes. Contrarily, the system depicted in Figure 4.3 takes an integrated approach, incorporating autopilot function buttons directly into another cockpit display. This design variation highlights the flexibility in the placement and integration of autopilot controls within different avionics systems, catering to the specific configuration and layout of the cockpit. Verification of autopilot function engagement. Ensuring the proper engagement of autopilot modes is crucial for verifying that the aircraft is following the intended flight profile. Autopilots typically provide clear indications of the currently active modes and may also display armed modes that become active when specific conditions are met, such as intercepting a localizer. The active modes are displayed on the front of the autopilot unit, just above the controls. On the other hand, the integrated autopilot currently engaged autopilot mode along the top of the primary flight display. This visual feedback allows pilots to quickly and easily confirm the status of the autopilot and ensure that it is operating as intended. How autopilot functions work. After an autopilot mode has been engaged, the autopilot performs two main functions. The autopilot assesses the specified flight profile entered by the pilot. This involves understanding the desired parameters such as heading, course, altitude, airspeed, or vertical speed. Once the autopilot has determined the necessary control inputs to adhere to the selected flight profile, it actively moves the aircraft controls, such as ailerons, elevators, and rudders, to achieve and maintain the desired parameters. Determination of control movements required to achieve goals. When utilizing the Autopilot FD, flight director, to execute a turn to an assigned heading of 270 degrees, the process involves a series of sequential steps. Initially, the pilot selects the desired heading using the heading knob on the Autopilot Flight Director control panel. Prior to initiating any control movements, the Autopilot Flight Director must determine the current state of the aircraft, including the present heading and bank angle. Subsequently, the system calculates the necessary parameters for the turn, encompassing the amount and direction of the required turn to align with the assigned heading. The flight director, Autopilot, then selects an appropriate bank angle for the turn, typically constrained to 30 degrees or less. This entire process relies on information gathered from diverse sources, such as the airspeed and altitude for current airspeed and altitude, the magnetic heading reference instrument for the aircraft's magnetic heading, and navigation systems that contribute to the calculation of turn parameters and assist in guiding the aircraft along the designated heading. Through the integration of these data sources, the Autopilot Flight Director ensures a precise and controlled turn, exemplifying the advanced automation capabilities of the aircraft. Carrying out control movements. After the flight director, Autopilot establishes the required control movements to execute a flight change. The next step involves the implementation of these movements. Autopilot systems are equipped with electromechanical components known as servos, which play a crucial role in actuating the aircraft's control surfaces. These servos serve as the muscle of the autopilot system, converting electrical commands into physical motion that directly influences the movement of the control surfaces. Through precise and coordinated action, the servos ensure that the aircraft responds accurately to the calculated control inputs, facilitating the seamless execution of the intended flight changes dictated by the Autopilot Flight Director. This integration of servos exemplifies the automated capability of the autopilot system in managing and manipulating the aircraft's controls to achieve desired flight profiles. Maintain altitude. The altitude mode of the autopilot is designed to uphold a designated barometric altitude. Upon engagement of the altitude mode, the autopilot endeavors to sustain the same barometric pressure, altitude, that the aircraft was maintaining at the initiation of the altitude mode. The process of activating the altitude mode for a specific autopilot is illustrated. Apart from ascertaining and executing the necessary pitch commands to preserve the assigned altitude, most autopilots possess the capability to trim the aircraft. An auto-trim system can autonomously make required adjustments to the pitch trim, ensuring the aircraft remains at the desired altitude and maintains proper trim. Notably, when the altitude hold mode is active, any applied pitch control pressure prompts the autopilot to counteract and trim accordingly. This feature enhances the autopilot's capacity to manage altitude control effectively. If you click like and subscribe and leave a comment, we will provide a coupon for a free PDF download, one of 9 ebooks. However, each individual can only download up to 1 out of 9 ebooks for free.